So I think it's 110. So I stole these slides from one of my colleagues just because these are fun facts. So equations of state that could be written as cubic equations with respect to the molar volume describe gas phase, liquid phase, supercritical fluid phase, right? So that's something sort of cool. And the other fun fact was that we saw that for these equations of state with two parameters that describe liquid, gas phase, and supercritical fluid phase, we have constants for being at the critical point. And that, of course, led us to, that sort of observation led us to say critical point's really, really important, and therefore we can say something about the law of corresponding states. We can introduce that, which basically says we expect all fluids to behave the same as long as we're looking at the same conditions relative to the critical point. All right, let's do a little bit of nitty-gritty, detailed stuff. Homework 4, how many people started at question number 1? No one. All right. That would have been a candy-worthy answer to say yes. All right. At any rate, get started on it. That's an Excel program that you have to calculate compressibility factors and plot them up. So that sometimes gets people into a little bit of troubleshooting mode, and it can be stressful. So start early on it. All right. The other thing to keep in mind is a week and a day from today is the first exam. So if you haven't started thinking about the first exam, this is a good time to start thinking about it. Take a look at the review materials that are posted on Canvas. There'll be a review session on Friday, 4:10 and 11:04. That's Brian is going to be handling that. And then Sunday, same room, same time, different day. That'll be Melissa. All right. If you plan, how many people are planning to go to one of those? I recommend that you download the review worksheet, right? Because if there aren't questions for Brian to answer, if you don't come there with questions, he's going to fill it in with other material, and that will be the source material. You okay with that, Brian? Okay, all right. Okay, so last time we met, we talked about the law of corresponding states, which we've defined at the outset here. We've said the way that we know where we are relative to the critical point is to look at reduced variables. So reduced temperature, reduced pressure, reduced molar volume. Those are all referenced to critical point, right? That tells us where we are. And then once we had that, once we defined these reduced variables, we were able to substitute those back into the van der Waal equation. And what we found as a result of our derivation is that we could write the van der Waal equation in terms of these reduced variables with no parameters. So that means that this is universally applicable, all right? And there's no R in there either. So this strongly supports the law of corresponding states, right? And we didn't take this and do the derivation for the compressibility factor, but you can do that and you end up with the same thing. You have an expression for the compressibility factor that's independent of the substance, right? You just need to know where you are relative to the critical point. We didn't do the derivation, but it can be done for the Redlich-Kwong equation of state as well, right? Okay, so from there we introduced the virial equations of state. We've pointed out that we can write out the compressibility factor in terms of a series expansion either in pressure or in the reciprocal of the molar volume. In order to do this, we've introduced these B's, and those B values are coefficients associated with the virial equations of state. So we call them virial coefficients. All right. We have pointed out that the B2, so B2V, B2P, those are related to interactions between two particles. B3P is between three particles. B4P is between four. If I go beyond that, it keeps going. Right? If we think about a gas phase, if we're operating at low pressures, we would expect that the most important interactions between our particles will be between two particles, because a three-particle interaction is going to be less likely, and four-particle even less likely, right? The other thing that we've noticed is that if we only worry about the first two terms, we can see that there's a linear relationship. Either the compressibility factor as a function of the reciprocal of the molar volume or as a function of the pressure. All right? And that's what I've shown here on the board. So we have compressibility factor on the y-axis. We've got pressure and bar on the x-axis. We know in the limit as pressure approaches 0, all of our substances behave ideally, so we go to a value of 1. Okay? The other thing to keep in mind is when we're using compressibility factor, that pressure, the molar volume, and the temperature, those are referring to our laboratory conditions. All right? And so that means it's not an ideal gas. Right? If it was ideal, we'd have a straight line, Z equals 1. All right? So those are real molar volumes, temperatures, pressure relationships. Okay? So if I look at the compressibility factor as predicted by our virial equation of state, looking at the first two terms, I have a linear relationship in pressure. The slope, therefore, of the line that's tangential to the compressibility factor curve will give me B2P. The other thing that we showed, and I've emailed out the derivation, we didn't go through the derivation, but there's a relationship between B2P and B2V. Simply RT is the factor that converts between them. So the slope of this tangent is given by B2V over RT or B2P. Make sense? All right. So in this case, I see a negative deviation from 1 at low pressures. What's responsible for that? All right. We'll do it as a multiple choice question. All right. Is it attractive? Well, go ahead. Attractive intermolecular forces. That is correct. All right. And where we go to a plus above 1, what kind of interactions do we have? That's repulsive. So after the box is here, pass it up there. Okay? All right. So in this case where we see this is a relatively low temperature compressibility factor curve. We see that in the limit as pressure approaches 0, I have a negative deviation and I have a negative slope. That reflects the attractive interactions. In this upper trace, where that's my compressibility factor curve, that's what we expect to see at high temperatures for a substance. So at high temperatures, we have large kinetic energies of our particles, so large that the attractive interactions are infinitesimal. They're meaningless then. All right? In that case, we see a positive value for the second virial coefficient. Okay? Does that all make sense? All right. So we're going to be exploring the second virial coefficient further today. All right. The other thing that we introduced last time was this equation that says this is B2V. What we note that we need to know, besides the temperature, is we need to know what the potential is. So we're going to be spending some time talking about potential interactions between our two particles today. Okay? All right, some things that we want to keep in mind. So this is from General Chemistry, Chem 1. If we're talking about the dipole moment is a quantitative number that reflects the separation of charge. So the two factors that are important there are the charges that are actually separated and then the physical distance between them. But from our perspective, what's important is that this is a numerical value. Okay? Now, if I have a molecule that is polar and we bring it in the vicinity of another polar molecule, then I can get interactions between those two molecules. So just very quickly review. If I have polar molecules that interact with other polar molecules, we call that dipole-dipole interactions. Right? If I have a polar molecule and a molecule next to it that's not polar, I can't have a dipole-dipole interaction in this example. But what I can do is say, this molecule has an electric field associated with it, and the electrons in this molecule will react to that electric field. Right? So in this end, I would see the electrons vacate, move in this direction, so I will get an interaction called dipole-induced dipole. So I induce a dipole moment in here. Does that make sense? Seen it before? Okay, so for clarity of showing the dipole-induced dipole interaction, I've said that one of the molecules is nonpolar, but it doesn't need to be nonpolar, right? I can have a polar molecule here, and the fact that I have an electric field here will still induce changes in the molecule next to it. Does that make sense? So I can experience a dipole-induced dipole between two polar molecules, and that'll be important in our discussions today as well. Now, if I have only nonpolar molecules, then I can't have dipole-dipole interactions. I can't have dipole-induced dipole interactions. But what we need to keep in mind is that this molecule consists of nuclei with electrons running around. Those electrons are moving around, and at any given moment, I can have more electrons on one side of the molecule than the other. And that's the definition of a dipole moment. All right? So if I have that situation, then I have a short-lived dipole moment, and if I have a molecule next to it, it can respond to that dipole moment. All right? Does anybody remember what those are called? London dispersion forces. Pass the box up, please. Okay? Make sense? All right, so we're going to be talking about equations that are associated with those interactions. And everything we've talked about with regards to these intermolecular forces were about attraction. All right, we will talk about repulsions as well. The other thing that I want to just mention is that we know that these intermolecular forces have some energy associated with them, right? And so my question to you is, are those forces stronger or weaker than the bonds holding a molecule together? How many say they're stronger? How many say they're weaker? How many aren't really sure? Okay, so let's talk a little bit about that. If I have water and I add heat to water and make it boil, I get little bubbles in the water, right? What's in those bubbles? It's gas phase water vapor, right? It's not hydrogen atoms. It's not oxygen atoms. So what we're saying is that our day-to-day experience suggests to us that I add energy to a system, I can overcome the intermolecular forces, but I'm not able to break the bonds, right? And so what we're going to see, or you're going to see in the homework problem, is that intermolecular forces are much weaker in general than our chemical bonds. Okay? All right, so things that we're going to do today, we're going to explore the relationship between B2V and intermolecular potentials. We're going to talk a little bit about how this changes with distance. We're also going to introduce a nice way to visualize what the magnitude of B2V means. All right, a nice physical interpretation. And then we're going to talk about these potential energies of attraction in mathematical terms. So we have that to look forward to. Are we excited? You're honest. No. All right. If she said yes, that would be candy worthy. Still can't make liars out of you. All right. I expected somebody to say yes. Yes. All right. Okay, anyways, where I want to pick up from right now is talking about B2V in terms of the potential. So we've introduced this equation. I wanted to look at one limit, okay? So what we see is that what we need to do is integrate over all the possible distances between my two particles, and we have this potential energy occurring in the exponential term, right? So if I let that potential energy be equal to 0, that means no interaction, repulsive or attractive. What is e to the 0 the same as? That's the same as 1. All right? So if I put 1 in for that term, I subtract 1 from it, it goes to 0, right? And so that tells me that if I have no interactions between my particles, attractive or repulsive, I expect my second virial coefficient to be equal to 0. Right? And that should make total sense, because if we come back to our virial coefficient, if that's 0, we're saying the compressibility factor is equal to 1, which is how we've defined an ideal gas. Okay? Okay, so the other thing that we recognize here is that if we know what the potential energy is, we can calculate the second virial coefficient. So then the question is, how do you determine what this potential is? Well, one way that you can do it is you can do some really nasty calculations using quantum mechanics. And we're not going to do that in here. Maybe next homework assignment or something. That's a joke. All right. The other thing that we know is that we can get it from the second virial coefficient. So the slope is equal to B2P, which is equal to B2V over RT as pressure approaches 0 for Z versus P, right? That's basically what I've talked about over here, okay? Looking at the tangent as P approaches 0, that where the compressibility factor can be described as a line, the slope of that line gives me B2P, okay? The other thing that we're going to do is talk about coming up with a function that describes the interactions, all right? So this would be something that's experimental or half experimental, half theoretical, all right? So and then you can fit your data to it, okay? So we're going to use the Lennard-Jones potential. How many people have heard of Lennard-Jones potential before? A few of you, right? It's also known as the LJ potential. It's also known as the 612 potential. Right? And in order for us to get some understanding of the Lennard-Jones potential, that's what this next slide is going to cover. Okay? So if I have my molecules or my atoms that make up my gases really, really far apart, we know they're not interacting. There's no attraction, there's no repulsion. They don't know that they're there. So at the limit, as R approaches infinity, our potential energy is 0. Okay? Now, as I bring those two molecules or two atoms closer together, then we know that they can experience dipole-dipole interactions, dipole-induced dipole interactions, London dispersion interactions. And those are all attractive. And so what that says is that as I bring these together and I have these attractive intermolecular forces, I see a decrease in the potential energy. Okay? All right, so from physics, what you find, let me write out a few things here. So for attractive portion of the intermolecular interaction, U of R, there is an R to the 6th dependence. All right? That describes the shape of this function. Okay? And we're just going to put in a constant there and say it's C6. Okay? All right. And now I'm going to introduce one other way to word this, or to indicate this, and that'll be sigma over R, all raised to the 6th power. Right? So it's pretty clear that sigma to the 6th is the same as that constant. Okay? All right. And we're going to elucidate what this sigma means in a little bit and over the next lecture as well. The only thing else that I want to indicate on here is that we see that this is a negative interaction due to the attractions. So I need to put a negative sign in there. So I have minus and minus. Okay? All right, then what we can do is say, well, as I bring those two molecules closer and closer together, what I start to see are the electrons on those molecules start to repel each other. And if I get close enough, the nuclei on those molecules start to repel each other. Right? And what I see then is a rapid repulsive interaction. Right? And it's clearly steeper than this. Okay? It follows that this is 1 over R to a large number, right? This is R to the 6th, R to the minus 6, so there's going to be R to the something greater than that, right? So you could use 1 over R to the 15th, 1 over R to the 20th. Those all work, right? Because it's this very steep function. For convenience sake, we choose it to be 1 over R to the 12th. All right, so the potential in this case is going to be positive. We're going to put a constant in there, C12. All right. And we're going to choose to use R to the 12th. When we compare these two, does anybody see the mathematical reason that this would be a nice number to choose as our larger number? It's the square, right? It's the square of R to the minus 6, right? And then further, this will be equal to sigma over R to the 12th. Okay? So whatever this value is, we just square it to get that value. Okay? All right, so what we've described are independently the attractive potentials and the repulsive interactions, and then bringing them both together, what we need to do is sum them together, right? And that's what's done here. This shows the summation, okay? And so what we see as a characteristic is, as I bring my particles closer together, I start to get an attractive interaction. When they get too close, it starts to repel each other, and I have a little well in there, okay? All right, that's the Lennard-Jones potential. LJ potential. And that is given by U of R equals. So we're going to introduce something new here. We'll talk about it in a minute. 4 times E sigma over R to the 12th. So right there, this is referring to the repulsive interaction. And now I'm going to add in sigma over R to the 6th, our repulsive interaction. Okay? All right. And then if I take the derivative of this function, set it equal to 0, what I find is my minima occurs at E. Right? So this E is the minimum of that potential well. Okay? And if we had two particles that were at low temperatures, we would expect that they would be sitting around that minimum value of E. Does that make sense? Okay? All right. And the other thing that we just want to reiterate is that this E is much less than the bond energy that is the energy that's holding two atoms together. So this is the difference between two independent particles and the energies of the atoms within a particle. Okay? All right, and you'll explore this relationship, homework 4, I think it's number 8. Yep. Okay? All right, so I said that we were going to try to get some understanding of what the sigma means. All right, so I want to do that also. So what we're going to do is we're going to say let sigma equal R. All right? So we're going to say there's going to be some value of R that corresponds to sigma. All right? When sigma and R are the same, what is sigma over R? That's going to be equal to 1. All right? What's 1 to the 12th? And 1 to the 6th? 1. Right? And that means this is 1 minus 1, or 0. Okay? And so basically that tells us that where we cross this axis is where R is the same as sigma. Okay? All right, so let's take a moment to talk about what that means physically. So let's say I have two tiny molecules, all right? So those two tiny molecules will come towards each other, and the repulsions are going to occur at this value of sigma, all right? So just put in your mind some temporary sigma, all right? Now let's pretend that I have two huge molecules, and I bring them together. And they're going to start to repel each other at a value of sigma. Will that sigma be greater or less than the sigma of my small particles? I'm talking about big molecules. Bring them together. Are they going to repel sooner or later than tiny particles? They're going to do sooner, right? Okay, so what we can say is that this curve shifts out for larger molecules. And for small molecules, it's going to be less. And so that, and we'll see this again from another direction, but what we can say is that this sigma is related to the size of our molecule. Okay? Does that make sense? Okay, so we're going to take a tiny deviation. We're talking about a physical interpretation of the second virial coefficient. So what we're going to do is we're going to be talking about this in the limit of low pressure. So this is talking about the linear region of the compressibility factor. That means that I only need to use two terms on my virial equation of state. That's what we've written there. Okay? Now this is written in terms of pressure, so I use the B2P. I know that B2V and B2P are related through this equation, and so I can rewrite this. There's my compressibility factor. That'll be equal to 1 plus, I'm going to put pressure over there, and then if I want this in terms of B2V, I divide it by RT. Okay? So I've just taken this equation and substituted in B2V for B2P. Make sense? Okay, so now we're going to take this equation, and before I move forward, let me just point something out. This is the compressibility factor. That's a real molar volume, right? I'm going to take that equation, I'm going to multiply both sides of it by RT over P. All right, so if I start looking at the left side, that's going to become PV bar RT times RT over V bar, or over P, sorry. Getting ahead of myself. All right, and what does the left side become? Just V bar, right? And because it's associated with the compressibility factor, we're talking about the real molar volume. Okay? Now I do the same thing to the right side, and that's going to be equal to, well, RT over P plus, and when I go to multiply this by RT over P, that gets rid of RT over P, or it gets rid of RT and P, and I'm left with B2V. All right, so I'm going to write very quickly PV bar equals RT. All right, so this is the ideal gas law. We've seen this a lot, right? What's RT over P if I keep in mind ideal gas law? It's V bar, but for an ideal gas. We agree? Okay. All right, so we can say, I didn't leave enough space here. Come down here, equals V bar ideal plus B2V T. Okay? And a very simple rearrangement. This says my real molar volume is given by my ideal molar volume plus the second virial coefficient. So the difference between my real molar volume and my ideal molar volume is the second virial coefficient. Okay? All right? And so this basically tells us that when we're talking about low pressures, the difference between my ideal gas molar volume and my real gas molar volume is the second virial coefficient, right? And that's reflective of us previously saying, when we see these deviations, pressure versus the compressibility factor, this is due to the difference in the molar volumes, right, between ideal and what we're actually observing, right? So that's explored further in homework 4, number 9. Okay? All right, the other thing I want to do is just take a look at this graph. So what I've got is a reduced temperature. It's a little bit more complicated than the reduced temperature that we've previously introduced. But the bottom line is it's still the reduced temperatures relative to the critical point. And here's B2V as a function of that reduced variable, the reduced temperature. And we've got argon, nitrogen, oxygen, a whole mess of different gases. And what we find is they all follow the same curve, right? And so this is just another observation of the law of corresponding states. If I'm looking at the second virial coefficient, the deviation from ideal, I see the same behavior as long as I'm comparing at the same point relative to the critical point. Okay. All right, in section 2.6, what we want to do is look at intermolecular forces and the Lennard-Jones potential that we've introduced. All right. So I'm going to start with the Lennard-Jones potential. So we've shown where this form comes from. All right. What I can do is I can multiply through by this 4 times the minimum energy of my potential energy curve. That first term sigma over r to the 12th reflects repulsive interactions because it's positive. And then this term reflects the attractive interactions. Okay? We see that there's an r to the minus 6 dependence on that potential. Right? So that's what we're going to be coming back to after we talk about the different intermolecular forces of attraction. So the first one we'll talk about is dipole-dipole. All right, so this is referring to two gas molecules. They may or may not be the same. All right. Again, we talked about this at the outset. So I have one polar molecule, another polar molecule. This interaction is what we're talking about. So if we go back to physics, we find that our potential between two dipole moments has a 1 over r to the 6th dependence. All right. It depends upon the permanent dipoles of the individual molecules. So permanent dipole moment. It's an attractive interaction, so we see a negative in front of it. Okay, right? And then we've seen temperature, we've seen Kb before. The only thing new that we're adding in there is this epsilon, right? And for our purposes, this is simply a constant. And you may have seen it in physics. It's called the permittivity of vacuum, or vacuum permittivity. And I've probably misspelled it, right? But for our purposes, it's just a constant, okay? All right, so the other thing I want to just point out, because I have two different dipole moments in there, this is a general equation. So this could be HCl and HF. It could be H2O and HCl, right? It just means I have two different dipole moments. Now, if I have two molecules that are identical, say two water molecules, these dipole moments will be the same, so I would have the dipole moment to the 4th power. Make sense? Okay. All right, so the next thing that we want to talk about are dipole-induced dipole. So dipole-induced. Again, we're talking about between two gas molecules. So our model is we have a molecule that has a permanent dipole moment. Next to it, the molecule reacts to the electric field caused by this dipole moment. That's going to create a dipole in the neighboring molecule. Okay? All right. So we need to define a couple terms. So E is the electric field that's experienced by one of our molecules, and that's going to be caused by the dipole moment in the neighbor. Okay? Right? And then what we need to know is how the molecule responds to that electric field. Right? And so what we do is we just introduce a new concept. All right? So I'm going to write out the equation. I've got the induced field is given by the electric field times this alpha, all right? And alpha is called the polarizability. How many people recall hearing about polarizability previously? When you guys talked about London dispersion forces, it should have shown up then, okay? So this is basically just a measure of how easily the electrons in this molecule react to that electric field. Okay? So it's a measure of ease of distorting the electron cloud. I tend to think of it just as mushiness of the electrons. Okay, so let's talk a little bit about this. So you may recall when you talked about periodic properties in general chemistry, as you go down the periodic table, the atoms get larger, right? And those atoms are larger because the electrons are further away from the nucleus, right? And as those atoms get further away from the nucleus, they're not as tightly held, as the ones that are close to the nucleus, right? And so what we can say is that as we increase the number of electrons, the polarizability is going up as well, because those electrons are further away. They're easier to push around. Does that make sense to everybody? Okay? All right, so polarizability increases with the number of electrons. All right, now I want to take this and extrapolate this a little bit, because we don't want to have to think about propane and say how many electrons are in it. Is there something else that we can correlate with electrons? And that's pretty straightforward, because what we know is that as the number of electrons goes up, what happens to the number of protons? That also goes up. And if you think about your nucleus, as you add more protons, what else do you add? More neutrons, all right? All right? And then if I said to you, I have an atom and I want to know its mass, do you want to know the number of electrons, protons, neutrons? What do you want to know the number of in order to know the mass of the atom? Protons and neutrons, because electrons are essentially nothing in terms of mass compared to protons and neutrons, or the nuclei, all right? And so what we can say is the mass also tracks. Right? So just very much in general, as the mass of my molecule goes up, that tells me the number of electrons goes up in general, and the polarizability goes up. Okay? All right, so now we have the conceptual underpinning that we can use in order to look at our potential. Right? And the first thing that you might notice is that we have two terms. Right? So let's just look at the terms real quickly. So this is the polarizability of particle 2, and then this is my dipole moment of particle 1. So that's going to be reflective of dipole moment, particle 1. So I'm going to call that particle 1. That will represent my permanent dipole. And then in my neighboring molecule 2, the electrons in there will respond to that electric field, and I will get an induced dipole. All right? So that refers to this interaction. And everything else that we've seen before. We've got the negative signs, we've got r to the -6, and we have our constant, the vacuum permittivity. The second term will correspond to, now molecule 2 has the dipole moment that's permanent, and then this will be our interaction with particle 1. Okay? Does that make sense? Okay, so let's ask a question. If I have two molecules that are not polar, what are their dipole moments? They're 0. So this will be 0, and this will be 0. And that means I have no contribution from dipole-induced dipole, which physically should make sense. Now let's say I have one molecule that has a dipole moment, and my other molecule doesn't, right? So that means my other molecule has a 0 dipole moment. So we'll say this one's the 0 dipole moment. So if I have one polar molecule, one nonpolar molecule, I only have one term, right? So I have two terms to reflect the fact that I have two molecules with a permanent dipole. Make sense? Okay? If these molecules are identical, then these are going to be identical, and this is just going to become minus 2 times one of these terms. Okay? All right, so that takes care of dipole-induced dipole. And then the last one is the London dispersion forces. This is London dispersion potential. All right, so I'm going to draw two molecules. All right, those are nuclei that I've drawn in just so that we're not limiting ourselves to diatomics, all right? And again, I want to talk a little bit about the origin of this. So we have this cloud of electrons. The electrons are moving around, and at some moment in time, I can get more electrons on one side than the other. That will set up a partial negative on that side and a deficit or partial positive on the other side. Then the moment that occurs, I now have an electric field that the molecule next to it can react to. right? And that will cause these electrons to move away, right? And the interaction there is what we're calling the London dispersion force, or London dispersion interactions, okay? So what we would expect is that the ability to have the induced dipole is important. So we've got, in two places, our polarizability. Polarizability of molecule 1, of molecule 2. Everything else up here, with one exception we've seen before, we're negative, r to the minus 6. We have to talk about I. I is the ionization energy. That's how tightly our electrons are held. Okay? All right, so I want to just take a moment, because polarizability is really, really important in this interaction. What we can say is that, how did I word this in my cheat sheet? So this interaction increases as particle mass increases. All right, and I want to put in parentheses that we know that the reason this goes up as mass goes up, or the reason that this goes up as mass goes up is because the polarizability goes up due to increase in electron numbers. Okay, and we've already talked that part through. Right? Okay, the other thing is that, you know, from Gen Chem 1, you probably learned that this is an insignificant interaction. How many people have learned that? Right? And it turns out that that's not quite correct. Right? So for most particles, most molecules, this is the dominant interaction. The exceptions to this general statement are for very small, very polar molecules. So exception. And those exceptions you've seen before. H2O undergoes hydrogen bonding, very polar. NH3, similarly. Okay? All right, and I do want to take a moment, and I'll include this in my announcements for today. I meant to put them in this set of lecture notes, but I've neglected to do that, so that'll be emailed out. All right, so this just shows if we're looking at intermolecular forces between particles, we can ask the question, what's the fraction of that intermolecular interaction that's caused by dispersion forces? So we start at the top of this table. Neon is atomic, it's nonpolar, so the only interactions it can undergo are dispersion interactions. Methane is nonpolar, so it also is only 100% is going to be London dispersion forces. But when we look at other molecules, methane and water, HCl, HI, even water and ammonia itself, we see that there's a significant percentage of the interaction that's caused by the London dispersion forces. Okay? So they are important, even though you may have left 177 not thinking so. All right. So we can put this all together and say, if I want to describe the potential attractive interaction between two molecules, I'm going to take the potential that's associated with the dipole-dipole interaction. I'm going to add to that the potential of the dipole-induced dipole. And I'm going to add to that the potential of the London dispersion interaction. All right? And so basically all of these terms that we've introduced get summed together. And that's what I've got down below. Okay? So this first term is going to be dipole-dipole interaction. This will be dipole-induced dipole, also dipole-induced dipole, and this is London dispersion forces. If I have two molecules that are completely nonpolar, dipole moment equals 0, that's the only term that I'll have. All right? If I have identical molecules, then I'm going to have the same dipole moments, and that means I'm going to be simplifying these. All right? You're going to explore that in homework 4, number 13. Okay? All right, so if we come back then to the Lennard-Jones potential, right, we have identified for E times this term to be the same as C6 over R6, right? And that's the attractive interaction. And that basically says that this term corresponds to that entire equation, okay? All right, and we notice that we've got this R to the 6th dependence in the denominator, and that further tells me that C6 is this equation with my R to the minus 6 pulled out. And that's what I've got below, right? So that's C6, which we know is also sigma to the 6th. Okay? And then if I square this value, that's going to get me my C12. Okay? All right. So now we have a way to calculate this potential. All right? Now if I want to use this potential to get the second virial coefficient, I'm going to take this equation, plug it in these appropriate places, put it in the exponential term, and then I'm going to integrate. Right? That's going to be homework number 5. I'm joking. Do you know how nasty that would be? Nobody's shocked. Nobody even passed out, all right? So it turns out that you can't analytically do this. You can only numerically approximate it. But what we can say at this point is we understand that we have a potential that we can put in there and that we can throw into the computer and make it crunch through it, and I can calculate B2V, okay? But we're not going to do it explicitly. All right. Okay, so what we're going to do instead is we're going to take this equation and we're going to say, well, what happens if I put a simple potential in there and try to get some understanding of the relationship, right? So section 2.7, I don't know what they officially call it, but I'm just going to call it simple potential interactions, okay? All right. We're going to start with a hard sphere potential. That's the simplest thing that we can do. That's basically saying, let's pretend our particles are billiard balls. All right? When they're not touching each other, there's no interaction between them. If I try to get them closer than their outer edges, I can't. All right? So potential is equal to what when they're not touching? It's equal to 0, no interaction, right? I bring them together, I try to put them on top of each other, I can't, so that means the potential goes to infinity, okay? And that's what's shown here. So in this region, potential is equal to infinity. Beyond that region, the potential is equal to 0, all right? The physical model, I've got one molecule, I've got another molecule, and the distance between those two is going to be how many radii? 2 radii, and we're going to call that sigma. Okay? All right, so keep in mind that what we're looking at is a potential that's infinity from here to here and 0 from here to here. So thinking about B2V, that means I need to break my integral into 2 parts. Right? Because I have 2 different potential regimes, right? So in this case, I'm going to integrate from 0 to sigma. And then for this portion, I'm going to go from sigma to infinity. Make sense? All right. Okay, before we do that, let's just talk about the volume of a molecule. So if we assume that it's a sphere, that means it's 4/3 pi r cubed. And we've said that there's a relationship between sigma and r, right? So r is equal to sigma over 2. So I'm going to put sigma over 2 in there. And then if I do my arithmetic, this becomes pi sigma cubed over 6. And that'll be the volume of one molecule. Okay? All right, unfortunately, that's where we're going to have to leave it for today. Thank you for your patience. Nobody got up to go. Nobody fell asleep. I'm shocked. We'll see you guys on Wednesday. Have a good afternoon.